It's time for another amazing chemistry video with Mr. Stapleton. Proudly sponsored by Finding a Nice Coffee.
Hi guys, welcome to this video today, which is going to be all about oxidation numbers. So it won't be too long a video, but I'm just going to introduce the 4 rules that we use when we're determining oxidation numbers, and we're going to use those when we look at redox chemistry. Okay, so when we're doing things like electrochemical cells, electrolytic cells, particularly when we're trying to write half equations or work out if oxidation or reduction has occurred, oxidation numbers will be really useful. So firstly, I'm going to go through the first 2 rules, which are fairly straightforward, so hopefully you understand them pretty quickly. All right. First rule is that the oxidation number of a neutral atom or monatomic molecule is 0. So what you've got to remember is what the prefixes mean. So if we're talking about mon, right, that means 1. So mono is 1. So 1 atom molecules. Okay, so I'll show you a couple of examples of those. But the rule is always if it has a neutral charge, the atom, or if it's a monatomic molecule, the oxidation number is 0. So a really easy example firstly of a neutral atom. If you've got something like a metal, so if you've got magnesium, okay, the oxidation number of the magnesium is 0. Okay, oxidation number is 0. What we normally do for oxidation numbers, we write them above the atom, okay, not to the side. This is where the charge goes, but we write the oxidation numbers above. So another example would be something like zinc, oxidation number is 0. Okay, if you had a non-metal such as sulfur, oxidation number is also 0. Okay, so that's just if you've got the atom by itself, there's no charge on it. Okay, the oxidation number is equal to 0. Now, a monatomic molecule is a molecule that's made up of only 1 atom. Okay, so the most common examples of these are like chlorine, nitrogen, oxygen. So all of those exist in this form. So chlorine is Cl2, oxygen's O2, nitrogen's N2. So you'll sometimes see these called diatomic molecules as well because there's 2 atoms within it. But in this definition, I'm talking monatomic, so it's only made up of 1 type of atom. Okay. So in chlorine, oxygen, nitrogen, there's no charge on any of these molecules. So again, the oxidation number of the chlorine atom here is 0. The oxidation number of the oxygen here is 0. The oxidation number of the nitrogen is 0. Okay, so all of those, okay, whether it's a single atom by itself or a molecule that's only got 1 type of atom in it, the overall charge is 0, so the oxidation numbers are 0. Okay. The second rule that we look at is this one here, which talks about that the oxidation number of a monatomic ion, all right, is equal to the charge. So again, what I'm talking about here is I'm talking about ions that are only made up of 1 atom. Okay, we'll get to what's called polyatomic ions shortly. Polyatomic ions are ones that are made up of more than 1 type of atom. But again, an example of this is if this time instead of magnesium metal, we had magnesium 2+, okay, the oxidation number of the magnesium is +2. So notice the difference between them there. The charge we write as the magnitude and then the sign, whereas the oxidation number we write as the sign and then the magnitude. All right, so the charge is 2+, the oxidation number is equal to that, so it's +2. Okay, if we had chlorine by itself, Cl- or a -1, okay, the oxidation number for that is -1 up there. Okay. So that's what we mean by just an ion by itself, okay? And you can have anything in there. So sulfur would be S2-, so the oxidation number is -2. So even I've written it the wrong way there, sorry. Thanks for picking me up on that. So the oxidation number of the sulfur will be -2 if it has a 2- charge, okay? Oxygen is 2- for its charge, so its oxidation number is -2, okay? So that's the second rule. Oxidation number of a monatomic ion is equal to the charge. So those 2 are pretty straightforward. Hopefully that makes sense. What I'm going to do is introduce you to then the following 2 rules. So the other 2 rules that I want to go through are this one, that the sum of the oxidation numbers in the molecule must equal 0, and that the sum of the oxidation numbers in a polyatomic ion must equal the charge. All right, so I'll deal with those individually. So first off, the sum of the oxidation numbers in a molecule must equal 0. So this is where you've now got a couple of atoms joined together, and I'm going to use some of the ones that we just went through with the first rule. So if we've got something like magnesium oxide. Okay, magnesium oxide. So we're taking a metal and an oxygen that we combine together, all right, to make a metal oxide. And we had a look before that the magnesium, when it was by itself, was a 0. When it's an ion, it's a 2+. All right? The oxygen by itself was a 0, but in ion it was a 2-. So it's kind of the same here because they've just combined together. This is made up of a magnesium, which is Mg2+, and an oxygen, which is O2-. Okay. Now the charge, the oxidation numbers on those, all right, in this case, are the same. So that's +2 and that's -2. Notice when you add those up, +2 and -2, you get an overall charge of 0. Okay. Now that seems pretty straightforward. Okay, and that's just easy because it's the same charge as they would normally have when they're an ion. Okay, so what I'm going to show you is sometimes the charge isn't always the same, so the oxidation number isn't always the same as what you normally expect for the charge. So what I'm going to do is I'm going to take sulfur as a really good example. I want you to see that there's a couple of different options that we can have for sulfur, and I'll explain why we have it that way. So sulfur normally is in group 6, and the ion normally exists as S2-, so the oxidation number is -2. Okay. Now you can find sulfur combined with a number of different atoms. Okay. So I'm going to have a look at hydrogen sulfide, H2S, all right, and then I'm going to look at sulfur dioxide, SO2, and I'm also going to look at sulfur trioxide, SO3. Okay. Now, the rule states that the sum of the oxidation numbers in the molecule must equal 0. So when we add all of these up, okay, these oxidation numbers for the hydrogen and sulfur, it must equal 0. These must equal 0, these must equal 0 as well. Now, one of the easiest ones always to remember is that hydrogen is almost always a +1. Okay, and there's only one exception for that, which I'll talk about right at the end of the video. But if you just remember that hydrogen is a +1, and the other rule to always remember is that oxygen is a -2. So if you remember, these two oxidation numbers for hydrogen is pretty much always +1, and for oxygen is -2. Okay. The only time that changes for oxygen is when they're combined together. And again, I'll explain that at the end of the video. So let's have a look at these ones. If we go with a hydrogen having a +1 oxidation state, it's like we're balancing up charges to actually put the molecules together. So there's 2 hydrogens here. 2 lots of +1 gives us +2 total oxidation for the hydrogen. So to balance that out, the one sulfur must be -2. Okay, that's because these add up. So 2 lots of +1, and then take 2 equals 0. So we're actually cancelling out the oxidation number. Here in sulfur dioxide, okay, oxygen is -2. Okay, so again, 2 lots of -2 gives us -4. To balance out -4, this time we need sulfur to be +4. Right, so in this one, the sulfur has an oxidation of +4. Up here, the sulfur had -2. Okay. Here we've got sulfur trioxide, SO3. Oxygen's -2. 3 lots of -2 gives us -6. To balance that out, the sulfur must be +6. So here we've got a sulfur oxidation state of +6. Okay. So the oxidation number doesn't always equal the charge. Okay. You've got to take into account this rule that the sum of the oxidation numbers in a molecule must equal 0. So that's when it has no charge. Now at this point, hopefully, what you're doing is asking, okay, well, why does sulfur have an oxidation number of -2? Why does it have an oxidation number of +4? Why does it have an oxidation number of +6? Okay, so what I'll do is I'll just rub these out, and I'll just explain that quickly because this is something important to know. And hopefully, you've watched the video around electronic configurations, okay? But if you haven't, I suggest you go and look at that. So sulfur has an atomic number of 16. So its electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p4. Okay? Now, the possible oxidation numbers that we talked about for sulfur just then was -2. Okay? We had one that was +4, and we also had one that was +6. Okay? Have a look at the pattern, see if you can work out what number is missing in the middle that I didn't show an example of. Hopefully, and if you've worked it out, it's actually a +2. Now, this is directly related to the electron configuration up here. Okay, and this is what we call the expanded octet rule. That sometimes things can expand their octet or decrease their octet if they need to as well. But what's happening here is that these oxidation numbers are directly related to this outer shell that we've got. Okay, so the sulfur here in this highest shell is the third shell, and in that shell we have a total of 6 electrons. Now what it would normally do is it would look to gain 2 electrons. Okay, if it gains 2 electrons, it gets a full outer shell of 8, and that's where we get our oxidation number of -2, or our 2- charge. What you can do is start actually losing out electrons through here. So if we lose 2 electrons, we get our +2. If we lose 4 electrons here, we get our +4. And if we lose all 6 electrons there to get our full outer shell, that's where we get our +6 oxidation number from, or a sulfur with a 6+ charge on it. Okay, so it can actually happen that it doesn't always equal the charge. It normally does, but sometimes it will actually go through a different oxidation number. So the 3 that you need to know, I'm going to put right here now. Okay, so the 3 that you need to know for the expanded octet rule are this one, which is sulfur. You need to know sulfur having an oxidation number of -2, +2, +4, and +6. You need to know phosphorus, which has an oxidation number of -3, which is its charge, +3 or +5. Okay, and then you need to also know chlorine, which has an oxidation number of -1, which is its charge, +1, +3, +5, or +7. Okay, so there is a pattern to these. Do you remember them? Here's the charge. Sulfur's in group 6, so it's a -2. Phosphorus is in group 5, so it's -3. Chlorine's in group 7, so it's -1. That's what you'd normally expect for a charge. What we then do is we take that charge and we make it the opposite sign. So -2 to +2, -3 to +3, -1 to +1. Okay, and then we add 2 to it, depending upon which one we're going with. So we add 2, 2, 2, we add 2 and 2, or we add 2, 2 and 2. Okay, or just 2 and 2, I should say that. So these are the only 3 you need to know. Okay, best thing to do is just to try and memorize them. Okay, but otherwise there is a pattern you can follow here of taking the charge and adding to it. And all of those are important because you need to remember that they can change their oxidation number when you're trying to use this rule of the sum of the oxidation numbers in the molecule must equal 0. Now, I know that that's a lot to take in, so you might want to stop and go back over that before you go to the final rule. The final rule is pretty straightforward because it just kind of links in the same. Instead of adding up to 0, we're adding up to the charge. So I'll show you what that means. And I'll use one of the ones that we've just been through. Alright, so let's just do a simple one to begin with firstly. So if we take the hypochlorite ion, which is ClO with a 1- charge on it, okay, we said the oxygen is always -2, so that's going to be a -2 there, okay. We've got something plus -2 equals -1, that's the charge we've got up here. Well, hopefully you can work out 1 plus -2 is equal to -1, so the oxidation number of the chlorine there is +1, okay. All we've done is worked out that the oxidation numbers here, -1 plus 2, must add up to the overall charge, which is -1. And that's what this rule is saying for us. Okay, so if we do one that's a little bit more complicated than that, let's do SO3 2-. Okay, so again, oxygen's -2. 3 lots of -2 gives us -6. So we've got something plus -6 is equal to -2. Okay, well, what you've got to add in there is +4. So in that case, the sulfur is in a +4 oxidation state. Okay, sometimes you can have even more things together. Okay, so you can have like the bicarbonate ion, HCO3-. Okay, again, just use these rules. Oxygen is -2, hydrogen is +1. So we've got +1 plus something, all right, minus 3 lots of -2 is -6, and all up that equals -1. So we've got 1 minus 6 is -5, and that's need to add something to it to get to -1, well, the answer to that is going to be +4 for our carbon. And so that's how we work out the oxidation number for the polyatomic ions, right, where we must equal the charge. So easiest thing you can do is just remember that hydrogen and oxygen, all right, are always +1 and -2, except in one instance each, which is the final thing I'll end for this video. Okay, so your hydrogen is going to be +1. The only exception to this is when it's combined with a metal, all right, unless with a metal. Now, metals only want to lose electrons, okay? Now, a hydrogen, a +1 for a hydrogen implies that that's lost an electron as well. So you can't have two things that lose an electron. So if you combine, let's say, sodium with hydrogen, so you get something like sodium hydride, okay? The sodium's going to lose an electron, it's going to have its charge of +1, okay? The hydrogen in this case can't be +1 because that doesn't equal up to our second rule, where the, our third rule here, where the sum of the oxidation numbers in the molecule must equal 0. We can't have a +1 there as well. So that, in that case, needs to be a -1. So if it's with a metal, the oxidation number is then going to be -1, and that's the only time it's different. For oxygen, okay, oxygen is always -2, okay. The only situation where that is different, hopefully you'll be able to work this out, is when it's with hydrogen. If hydrogen is always +1, okay, in the case where you get hydrogen peroxide, H2O2, again, the sum of the oxidation numbers in the molecule must equal 0. So if the hydrogen is +1, the oxygen here must be -1. So in hydrogen peroxide, the oxidation number of oxygen is -1, and that's the only time it's not -2, all right, when it's combined with the hydrogen like that. So hopefully you've understood a little bit about oxidation numbers, and it's makes a little sense for you. Okay, suggest you maybe go back over and have a look, particularly around some of the oxidation numbers in molecule equaling 0 with the expanded octet. And as always, if you've got any questions, ask me. Thanks, guys.